Okay. So welcome to Math 460, 560, numerical analysis. So 460 for undergraduates and um, 560 for graduate students. Um, the numerical analysis one. So just for today, because of a COVID-related situation that thankfully has resolved itself happily. Um, Today's class meeting is virtual. Contrary to what I said in Canvas, announced at Canvas the other day, um, I will be teaching this in person. I'll be in the classroom starting this Thursday. So only this class period today will be virtual, in person after that. Now, all semester long, no matter where I am, all of you have the option of um, either attending virtually as you are all doing today, or you can show up in the classroom in Hattiesburg or the classroom at the Gulf Coast. The only thing to be concerned about, as I mentioned in Canvas announcement, is that we do not have too many people in the Hattiesburg classroom all at one time. Now, some of those Hattiesburg enrolled students I already will not be present because they are actually based at the coast. So maybe it won't be an issue, but we'll just see what happens on Thursday. And I figure there's some of you who prefer to be in person if at all possible, and then some of you might actually prefer virtual. So, in the interest of accommodating everyone, and also in the interest of safety, which um, I would like to prioritize, um, that so whatever you want to do. Okay, so um, before I get into any I'm not going to really do much in the way of raw material today. I'm going to, of course, discuss the syllabus and give an overview of the course and about numerical analysis in general. Um, so what I need to do first is acquaint all of you with the uh, two websites that I have going for this class. So let's get the screen share going. Okay. Mm. Okay. Um, so first, dealing with Canvas, starting from the course homepage. So from this page, as you probably just did, um, that you can always click here, and it'll take you to the Cisco WebEx meeting. So this is what I'll have for every single class. Um, WebEx doesn't let me schedule on the quarter hour. That's why it says 5:30 to 6:50. But class actually runs from 5:30 to 6:45, as I'll have noted here. And um, so I'll generally post like the coming weeks meetings here that you'll see in upcoming. I just haven't done Thursdays yet. Past meetings here, I was just playing around, learning a technology, and recorded meetings will show up here. Um, I don't know for sure yet exactly how long it takes. For instance, when I did these two as a test, um, I didn't actually see them in here under recordings until the next day. I'm not sure if it really does take that long, but it takes some time. What I should be able to do, as I've done in other classes, is also download the recording afterwards and put it up on YouTube, and that's something that apparently will be done a lot faster than what you see here. Okay. Also, um, for for each class meeting, I have a link here that actually takes you to a discussion item. Um, and before class, it's just a link to the same thing that you saw earlier with Cisco WebEx meetings. But what I will put in here for each class period after class, it'll probably be that evening, but or if not, certainly by the next day, is whatever notes I was preparing during class will be posted here after class. Also, a link to the uh, a link to the video for that class we posted here. I mean, you can access them under Cisco WebEx under recordings, but you can also access them here. Now let's see what else we have in Canvas. Okay, under assignments, you can find all of them here. Actually, I don't even need that group. So all the assignments for the whole semester are already posted, due dates and everything. So what we have in terms of coursework, we have online quizzes. These are quizzes in Canvas that are a short answer. The questions are taken directly from the textbook, but they're just reposted here. So in the book, there's a concept check questions. So I take not all of the questions, but most of them, and those are the quizzes. These are generally due around the time that the corresponding topic is covered. Now, the idea is that shortly after the topic is covered in class is when I would like you to do the quiz. It's largely a reading quiz. It gets you to look at the material in a textbook. So generally what you could do is you could find the answers from the section. So hopefully these questions are relatively quick. They're largely about definitions, fundamental concepts, properties of certain algorithms that we'll be learning about, things like that. Okay. So here we have the homework assignments, and these will generally be due roughly 1 week after the corresponding topic is covered in class. So these are problems referred to as explorations that are taken from a textbook. So for example, if I look at homework 1, so section 1.2, problems are labeled in the book as explorations. So you can get the list here. All assignments are submitted by uploading files to Canvas. So some problems will be the kind worked out on paper. So you can, for instance, scan your pages into images or a PDF and upload that. There'll also be coding problems. The preferred language is MATLAB, but if you really do want to use another language, you're welcome to do so. So your code can be would also be uploaded to Canvas either as individual files or as, if you want, you can zip them up and upload that. That's fine too. Because your code I'm going to download to my computer and run anyway. And then for other assignments, there will be a midterm and final exam. Because we're still, at least to a certain degree, teaching in COVID mode, these will be take-home exams. So I'll have more information about those when it gets closer to that time. And also submitted by Canvas. I said some enthusiasm about that. Okay. If there's anything else I need to talk about specific to Canvas. Okay, so you see here it says, okay, click here to go to the course website. And you might think, well, this is a course website. Well, there is another site, but the information you can get from either one. But I'll just show you what you have here anyway. So this is the course website I'm referring to, because before I was doing things in Canvas, I always had these course websites under the math department web server. So you can find here the syllabus, but that's also in Canvas, and also the lecture schedule. And unless there's something like a natural disaster, I am going to try my best to stick to this schedule where you can see all the due dates, what section of the textbook is going to be covered that day. Everything is planned out for the whole semester. Okay. Oh, this is the official final exam time, but I just said the final exam is going to be take home, so that this time information can be disregarded, but it'll be due sometime during this finals week. Okay. All the assignments, I've only posted the first one here, but the rest will be posted here. But this just mirrors what's in Canvas. Another feature that I have once you get going with homeworks is the questions page. So if you send me a question about the homework, and it appears to be a question that would be of general interest to the class, then what I will do is I will post the question here without the student's name, and then my response. So that way everyone can benefit from this question. So if you're asking a question, you may well be helping not just yourself, but also your classmates. Yeah, I don't have cats anymore. These are cats I used to have, but here we are, cats. I actually have a dog now, but I do not have pictures of her up on the site yet. I should do something about that. Okay. All right. If any mistakes are found in material, they'll be posted here. I should mention, if I go to my main web page, so I have a page here about the textbook. So this, yes, I wrote a textbook in collaboration with Amber Sumner, who was my PhD student a few years ago. And I have been maintaining a list of known mistakes. So I apologize for how many mistakes have been found. Some of these will be in chapters that we won't be covering, but it's something to keep in mind as we go through each chapter. Okay. All right. Also, show under courses. So yeah, this every course I've ever taught at USM. So what you would find is, since I've taught this class several times, you can actually access archived versions of the site. So sometimes there's, I might find useful information posted there. Also, you might find something useful here about other classes that I've taught that you might happen to be taking. Okay. Okay. I want to return to the syllabus. Okay. All right. Okay. Now, as far as the prerequisites, funny thing is, these are the official prerequisites that you find in the USM catalog, but we won't actually be doing anything in this course that involves multivariable calculus. And we won't be doing linear algebra either. I can say that the sequel to this course, Math 461, 561, that I'll be teaching in spring, will rely on linear algebra pretty heavily. Okay, the textbook info, and then here's how the grade will break down. So the homework here, that category consists of the homework assignments that are the explorations from the text and the quizzes. So all of those items will be lumped into this 30% category, and each one weighted equally within that category. Okay. And usual required syllabus statements about disability accommodations, academic honesty, and sadly, COVID. Okay. Now, before I go any further, does anyone have any questions about how the course will be run?
Dr. Lambers, with regard to submitting homework, if we've typed up results, can we submit both a PDF and an M file with our code?
Oh, sure, absolutely.
Okay.
Yeah, in fact, I like it when students submit PDFs of things. So you're talking like typed up. I recall you did in another class. Because then it's definitely easier for me to follow. Uh, Speaking of coding, so what I'm going to be doing during the first part of a course is so starting on Thursday and for 4 class meetings, I'll be introducing MATLAB. It's important to spend a lot of time on that because I'm not assuming that anyone has that knowledge coming in. And if you're helpful, if you have experience in other programming languages, that's helpful. But again, I don't like to assume. And so that's meant to prepare you for MATLAB problems that you will do later on. And one of the most preventable causes of losing points on MATLAB problems is that someone writes some code that's required by a certain problem, and then they don't bother to test it. You can tell, I could tell that the student has not run their code at all, because I try to run it, and there's a runtime error, and it could be something like a simple typo, maybe a parenthesis out of place, something like that. That if they had bothered to run it and gotten that error message, then it could have gone in and fixed it. So always actually run the code you write. Test it on a simple example, and oftentimes I will recommend a way to test whatever you're writing for a certain problem. So be sure to take the time to do that. It really will be worth it in terms of avoiding lost points. All right. Now, okay. What I'm going to do here is, from here, I'm going to go to my notes. I'm going to temporarily unshare. Oh, okay. Okay, now see we have 20 out of 23 students here. So unfortunately, that's not everybody, but we'll see what happens with that. Okay. Now, what I'm going to be doing, because unfortunately, even when I'm in the classroom, Southern Hall 303, and also because we have 4 students on the coast, from time to time, I will head down to the coast and teach in person in that classroom and have myself video conference up to Hattiesburg, just so we have in-person teaching to some degree for both Hattiesburg and coast. But unfortunately, in those classrooms, it's not feasible because of a video conferencing to use the board. And when I first started having students in Hattiesburg and the coast, both for this class back in 2017, I tried various ways of delivering the content, and none were ideal. But what worked best, and what I'll be using this time, is I'll show you here. And some of you would have seen this in other classes that you've had with me. Okay, here we go. Okay, so this program, Bacoma Tech Word, since LaTeX is a great way to present mathematical content, it's what people use when writing papers. Oh, I don't know if I can access the chat from here. Okay. Sorry. Okay, this is a bit of a pain. Oh, okay. So I need to catch up to what's going on in the chat. Oh, yes. I will announce when I will be making appearance at the coast beforehand. Okay. All right, let me get rid of a chat. Okay. So when mathematicians are writing papers, making presentations, and so forth, LaTeX is a generally accepted way to prepare that content, and that's what I'm using here for this class. And any other class where it's not feasible for whatever reason to use a chalkboard or whiteboard. So what I do here is I'm typing my content down here in this lower left corner, and it's immediately rendered here in the main part of the screen. Sometimes it behaves in a way that I don't like, and you'll hear me fuming about that. I apologize in advance for that, but it's just one of those things. It will happen. And so this is what I'll be using, regardless of whether I'm teaching virtually as I am today or also in the classroom. And this will be shown on the screen in the video conference classroom. Other times I'll be doing MATLAB demonstrations and therefore sharing my MATLAB screen. Okay. So things to keep in mind for this course, which are not necessarily the same as other upper level math courses. Okay. Now, so I want to point out, and this is really true not just of this course, but other upper level mathematics courses. Because I recall from my experience in teaching classes such as Calculus 1 or 2, what's really nice about those classes at a lower level is that there's always time to do a ton of examples of things like computing derivatives and integrals and so forth. And each example doesn't take a very long time. But as you start getting to upper level classes, even something like slightly higher levels, such as Calculus 4, that whatever examples you're doing tend to be a lot more involved, take a lot more time, and therefore there's not as much time, not many examples can be fit into a class period. It's the higher level you go in mathematics, and certainly at a 400 level mathematics course, that more abstraction is required to take what is learned from a given example and figure out how that applies to other examples or homework problems. So that's something to keep in mind. Again, not just for this class, but for this level in general. Now, this is something that's come from from my experience of teaching at USM. One thing that I often hear students say is they'll tell me that they feel like out of a whole class that they're the only ones not getting a material. And what they base that on is seeing how, okay, they're sitting there, they're confused, and they see that no one is asking questions. So what if they make this assumption that their fellow students who are not asking questions are not asking questions because they're understanding everything, while they themselves are sitting there not asking questions because they're confused. So why would it be different for you versus everybody else? So it's really closer to the truth to go with this assumption. If you must make an assumption, I suggest you make this one. So now, obviously, that's not what I want, but this takes me to my next point. Okay, actually, this time unit time no longer applies. I should say 75 minutes. So during this hour and 50-minute class period, it may be true in a lower level class that you're sitting there during that 75 minutes, and by the time that class ends, that whatever is presented is like, okay, I get it, I'm good with it, you're ready to plunge into the homework. Again, it's true of upper level math classes in general. Don't expect it to happen. Just because it doesn't happen doesn't mean that you're hopelessly lost. This is where asking questions is important, and to try to firm things up. And that's why I have a questions page on the site for homework questions that may be of general interest. There's also why I have the Canvas quizzes, the concept checks, that are used to reinforce whatever is presented in class. Okay, and this is a big one because what I found, I've taught at 4 universities, and I've been here for 12 years. So certainly the longest stretch here. And there are certain traits that I've noticed USM students have compared to students elsewhere. One trait that I've not listed here in these notes, y'all give up on tests way too easily, like way too quickly. And another is that they are that USM students as a breed are terrible about asking for help. I know there are various hangups of doing that as far as like, and who knows what those hangups could be. I'm familiar with some of them at least. It's something you got to find a way to get past. And you don't necessarily have to ask in the middle of class. If you want, you can contact me after. I try to make myself as available as possible for that. Um, and certainly the higher level you go, the more important is to do that. So I've heard students say, "Oh, I don't want to bug him. I don't want to bug Dr. Lambers. Bug me. I'm giving his commandment in all caps. Bug me." So this is how we get everyone through this class. Okay. All right. Yes, everyone follow Taylor's example. Okay, so very quick info about me. Like I said, I've been here for 12 years. Got my bachelor's literally 30 years ago. So yes, I am ancient. Um, thank you, Walker. And I made it was a double major in mathematics and computer science, and then got my graduate degrees at Stanford in an interdisciplinary program, scientific computing and computational mathematics. So it was a blend of numerical analysis, this topic, and applied mathematics and computer science. My research specialty is the numerical methods for partial differential equations. The class we have on that is Math 721 that I recently created. Those of you who have taken Math 417 or 517 learned about PDEs in that class. Okay. Um, so, um, So what I want to do during the actually, you know what? Okay, there's something I forgot to do in my Ever class. So I want to try to remember to do this each time, and feel free to remind me because we have a 75-minute class period. What I'd like to do is go for 35 minutes, as I've just done, exactly, and then take a 5-minute break, and then I'll pick up for 35 more minutes, and that adds up to 75. So, and this is a natural place to do that. So, um, okay, so I'm going to, so let's break for 5 minutes ish. Oh boy. Okay. I just majorly goofed here. because I went ahead and resumed recording, and I just started talking without turning on my video or unmuting myself. So I was actually teaching for about 2 or 3 minutes, and no one was able to see or hear me. So that part will actually show up in the recording, I believe. I'm not sure, but it doesn't matter. I obviously have to do it again. Thankfully, I didn't get very far. So like, I saw Xiaodong's question, shall we start the second session? It's like, what are you talking about? I've already started the second session. I just had forgotten to include all of you in it. Sorry about that. But like I said, I'm getting accustomed to Cisco WebEx. This is literally my first time using it for a class, but at least this is a good time to get all the kinks out. Okay, so actually, I'm going to move this to let me change how I've paged this. Okay. All right. Um, okay. Um, Now, so in a nutshell, this is what numerical analysis is. That um, it's all about numerical methods for solving a kind of math problems that you're already familiar with from other courses. Problems that come from calculus, such as derivatives and integrals. Linear algebra, such as solving systems of linear equations or computing eigenvalues of a matrix. Or solving differential equations. And other areas of problems from other areas of mathematics that build on problems from those areas. You're accustomed from other courses to using analytical methods, methods that use human beings' higher level reasoning skills, ability to recognize patterns, ability to abstract, and so on. Whereas numerical methods cater to what a computer does best: add, subtract, multiply, and divide ad nauseum and very rapidly. So these methods are of a very different nature because of who or what is actually doing the work in one case versus the other. Now, methods that you're familiar with from other courses, you might not really have referred to as analytical methods. So I'll give a few examples so you have a point of reference. As an example, from Calculus 2, using a fundamental theorem of calculus to evaluate an integral by taking the antiderivative and substituting in the limits. Or if you're using Gaussian elimination to solve system linear equations, for example, from Math 326, performing row operations, etc. Also, suppose you have a inhomogeneous second order linear differential equation with constant coefficients like this one. In Math 285, you'll learn how to solve this problem using a method called the method of undetermined coefficients. A second method is variation of parameters as taught in that course. Um, so, so these are the kind of approaches you would take to solve each of those problems on paper. So between either this course, 460, or the second course, 461 in the spring, you'd actually learn how to solve all of these problems and others like them using numerical methods instead. So the two types of methods, analytical or numerical, have different purposes because they have very different properties. Because when you have an analytical method, um, it's generally only applicable to certain subcategories of problems. So, um, so you already know analytical methods for evaluating certain kinds of integrals, and you covered a lot of them in Cal 2, integrating polynomials, basic trig functions, certain combinations of trig functions, or anything you can do by U substitution to reduce it to a simpler integral, integration by parts, partial fractions. But all of those methods you learned in Cal 2 will be of no help whatsoever in evaluating this integral. You can try all the techniques you want. It's not happening. As for it's actually been proven that there's no antiderivative of e to the minus x squared using elementary functions. Now, if this is e to the minus x, you could do that. If this was x e to the minus x squared, you could do that too, but not this one. But still, this is a very important integral. Gaussian functions pop up in many areas of mathematics, in statistics, partial differential equations, etc. So this integral is still of importance. You just can't do it the way you're accustomed to. solving system linear equations. In Math 326, which I taught recently, probably for most equations I'd have a student solve in a problem like a system maybe no more than 5 equations. What if you have literally 1 billion equations? And yes, in some places, people are having to solve systems of equations that have this many equations. Now, you know how to solve ODE like this if P and Q, the coefficients, are constant. What if I change the problem just a little bit? I replace this constant P with e to the x. The analytical method, you're not going to be able to use to solve this problem. Undetermined coefficients or variation parameters, no help. But a numerical method can solve this. One more example that'll be relevant toward the end of a semester. From, if you remember your trigonometry, you can solve an equation like this. So, for example, if one solution would be x is equal to pi over 3, or 60 degrees, and the other values because of periodicity. But if I take this equation and simply multiply the left side by x, so solving equation x cosine x equals 1/2. Whatever you learned in trig or algebra or any other math course is not going to help you solve an equation like this analytically. But toward the end of the semester, you'll learn how to solve an equation like this numerically. Right. So to contrast the two types of methods, pros and cons to each. I think I hear someone unmuted. Is there a question? Okay. So analytical methods, the benefit is whatever problem you're applying it to, you can get the solution exactly. But you can only do that for so many categories of problems. Their applicability is rather narrow. Numerical methods, total opposite. You can so you can apply them to far more problems that you could never use an analytical method for, but what you get is an approximation. And so a lot of numerical analysis is a study of approximation and error. If you're using a certain numerical method to solve a problem, you'd like to have an idea, be able to quantify how accurate is the answer going to be. Is there an upper bound on how far off the answer could be? Is there an upper bound on the error? And in some cases, we will be able to determine that. And we actually rely on what you've learned in other courses. For example, certain concepts from calculus, such as Taylor polynomials or the mean value theorem, are very helpful in numerical analysis for building the theory behind it. So when what you're going to learn in this course is how certain numerical methods are designed, and then later implemented. So both stages we focus on here, and also how to analyze them, their effectiveness. So there are 3 criteria that a numerical method needs to meet. Obviously, we want it to be accurate. And I ask here, what does that mean? Because that's actually dependent on the context. Because in some cases, you would like a solution that's accurate to as many decimal places as you could possibly obtain. Maybe something that's accurate to, say, 15 decimal places or so. In other cases, because of the underlying application, you might not really need that much accuracy, because problems in mathematics come from some sort of mathematical model for some real world application. Like, for instance, modeling some kind of physical phenomena like diffusion of heat energy or propagation of sound waves, things like that. And in any kind of model that comes from a real world application, there's always going to be some level of uncertainty. So if there's already a lot of uncertainty in the model, then there might not be a point to trying to solve a model to very high accuracy, because sure, you've achieved very small error, and you think, okay, that's good, but if there's already large error because of something else and you can't do anything about it, then why expend extra effort to get high accuracy in this in one respect that's not really going to help you? So sometimes you can obtain solutions more rapidly by having a realistic standard of accuracy to shoot for. So it's not always a clear-cut thing. It's not always going for the most decimal places you could possibly get. And this relates to the second criterion, efficiency. So these two have to be balanced. That you like to get your answers quickly, but efficiency is not just about how much time something takes. There's also storage space. A lot of problems involve huge amounts of data, and you have to think about how that data is stored. These days, we're all about big data, and there's so much data that's being obtained that storage of that data has become a huge problem now, just because there's so much of it. And what if it can't be readily accessed? Then that's something that certainly hampers efficiency. And then a criterion that can sometimes be overlooked at one's peril is the numerical method robust? Or I like to use the term reliable, but a lot of people refer to it as robustness. In a nutshell, what that means is, suppose you have a problem that your numerical method can solve, but then the input of a problem is changed slightly. That should not lead to a large change in the answer. If that happens, then either the problem itself is poorly posed. We'll talk about conditioning of problems in the second chapter, or maybe the problem is okay, but the method is not. Maybe you have an unstable algorithm, and that's something that can certainly happen in a poorly designed numerical method, and therefore that method is useless because you're in a situation where you simply can't trust the answer that it's giving you. So as we consider various problems in this course, we'll consider all of these criteria. Okay, so as far as what's actually going to be covered this semester, as I mentioned earlier, first I'm going to spend a lot of time on MATLAB to get everybody up to speed with that. That's section 1.2. So the first homework assignment will be on that. So you have plenty of time before that assignment is due, but that's because the assignment is rather large. So as we get into MATLAB starting on Thursday, as I get through like 1/4 of a tutorial, you want to get started on those homework problems related to that sooner rather than later. Next, we get into general principles of error analysis. What are the different types of error? How is error measured? What does it mean for a problem to be well-conditioned or ill-conditioned? What does it mean for an algorithm to be stable or unstable? And then what you might find one of the more interesting parts of error comes from computer arithmetic. So that becomes a serious issue because every arithmetic operation that a computer performs is going to have at least some error involved. Generally, that error is very small, but not always. An error incurred through a large number of operations can accumulate. And so you get an answer that's totally nonsensical. So you get an understanding of how computer arithmetic works, how to quantify the error involved, and how certain computations may need to be changed to reduce the rounding error that occurs. And this is where you're going to learn that there is an alternative version of the well-known quadratic formula that computers need to use. So this is one case where you see a sharp contrast between numerical and analytical methods. Admittedly, this part gets more computer sciencey than the rest. Beware. Then we get to certain general problems that are important building blocks in numerical methods. Polynomial interpolation. If you have a certain number of points in the XY plane, how can you find a polynomial that passes through all of them? So you'll learn various algorithms for doing that has their own pros and cons. And also certain kinds of polynomials, such as cubic splines, that can possibly fit a set of data more effectively. Then we'll get into numerical methods for problems in calculus. How do you approximate derivatives and integrals? And these methods relate very closely to polynomial interpolation because polynomials are the easiest functions to differentiate or integrate. So the basic idea is you approximate if you want to integrate a function, for example, you approximate it by a polynomial, and then you integrate the polynomial exactly. But we also want to get an idea of how accurate that approach is, and what are certain variations of methods that can deliver more accuracy than others. What you'll find is that, like, we'll learn several approaches to solving these problems, but no one method is the best in all cases. And part of being knowledgeable in numerical analysis is knowing which method to select for a certain kind of problem. We'll end the course with chapter 10, nonlinear equations, basically root finding. So if you have an equation of a form f of x equals 0, and that equation cannot be solved using algebraic manipulations, like some of the equations I showed earlier, we'll learn about iterative methods for solving these kind of equations, such as bisection or Newton's method that you possibly might have seen in calculus, depending on your instructor's preferences. And if you get through all this and have the stomach for the second course in the spring, problems that will be covered there feature problems from linear algebra, systems of linear equations, also methods for ordinary differential equations, initial value problems, boundary value problems, and also systems of nonlinear equations, building on what we learned about solving a single nonlinear equation here. All right. Are there any questions up to this point, just about the overview of the course, what the course is about? Okay. So what I want to do to conclude today is give an example of a real-world application of numerical analysis that shows just how crucial it can be in certain real-world settings. Okay, now, so this comes from wartime. So in the 1991 Gulf War, we had to contend with Iraqi Scud missiles, and we dealt with them by intercepting them with our own U.S. Patriot missiles. So the idea would be that you'd be tracking the Scud missiles on radar, estimating their trajectory, so then you would know where to fire a Patriot missile to intercept it. Now, the idea here is you're just estimating its velocity using this formula. The velocity would be approximated by taking its change in position, because its position at various times would be known, and then dividing it by the difference in time. So velocity is the displacement over just a change in position over change in time. So this seems nice and straightforward, right? And then and generally this worked very well, and so we would successfully intercept those missiles. But there was one occasion where it was unsuccessful, where even though before the Patriot missile would hit Scud, it missed wildly, and Scud missile got through, and sadly, 28 American troops lost their lives because of this misfire. And it would seem rather odd that something that would work most of the time, this one occasion would fail, because there didn't seem to be any indication of something wrong, like with the equipment, bad parts or something like that. So if it wasn't anything like that, what could it be? And this is something you can actually look up online, all the details of the investigation that ensued to try to figure out how this could happen and how to prevent it from happening again. So, and they actually figured out what the problem was. It actually came down to this, the difference in time. You might think, well, what could possibly go wrong with that? I mean, it's just performing subtraction. And yes, I did mention that any arithmetic operation carried out by a computer does have some error, but like I said, that error is generally very small. And that's generally true. but not for subtraction. And this is something that I'll get into more when we get to section 2.2 on computer arithmetic. So what happens is, at first, let's suppose you started tracking equipment and you're marking time starting from 0. And therefore, you're subtracting pretty small numbers here and getting a small difference in time. At first, everything works just fine, and you have successful missile interceptions. But over time, as you leave the tracking equipment running, these numbers, T1 and T2, get larger and larger. I mean, you're still subtracting them. And when you get to a situation where the difference between two numbers is a lot smaller, it's this symbol you might not have seen before. When you have a double less than, that means much less than. And yeah, that is not precisely defined. But so when you're subtracting two relatively large numbers that are close to one another, so when you have this situation happening, then you could actually get a result that is terribly inaccurate. And this situation is called catastrophic cancellation. And in this case, it was sadly, literally catastrophic. So once they recognized that this was a problem, that you're subtracting these large numbers that started out small but eventually got large, how do you handle it? What their solution, and this worked, was to restart the tracking equipment every 8 hours. Now, why would that work? Because they determined that by only letting it run this long, that would place an upper bound on how large these numbers could get. And yes, when counting, for instance, 8 hours in terms of seconds, there would be some error involved in subtraction, but they found that by limiting the size of the numbers to this, that it would be like an acceptable bound on how much error would be incurred by the subtraction. And therefore, they could be assured of a successful interception. And that turned out to be correct, that there was no other incident like this for the rest of the war. Yeah, that's literally what happens. Turn it off and turn it on again. Yeah, because before I'd been running for far longer than 8 hours, and those numbers got too big. So as for how this actually happens, how this leads to large error, that's something I will get into when I get to that section, and how certain computations can be modified when they have a problematic subtraction like this one to avoid that. And that's where we get into that alternative quadratic formula, because a quadratic formula involves a plus or minus. And in certain situations, one of those roots, a plus or a minus, can be inaccurate. So you can modify quadratic formula so that, for instance, if a plus is bad, it becomes a minus, and that fixes the problem. Okay. So this gives you an idea as to why numerical analysis is a particularly important area of mathematics. It's also a very employable area of mathematics. So in terms of career opportunities, scientific computing, computational science, numerical analysis, these are all roughly synonymous, is the most rapidly growing area in terms of career opportunities. And yet, based on a typical math curriculum, a lot of students are not aware of the existence of numerical analysis, usually until they're seniors in college or possibly graduate students. And I think it'd be nice to have some exposure to numerical analysis earlier in one's education to be prepared for such career opportunities. And that includes in Mississippi. There are jobs available for students at various levels, bachelor's, master's, PhD, at least for U.S. citizens, in government labs in Mississippi, such as Army Corps of Engineers Research Center, or Naval Research Lab, or Naval Oceanographic Office, but also outside of government, such as Ingalls Shipbuilding on the coast has use for students with background in this area for like internships or careers. So for that reason, it's particularly helpful area of mathematics to know, because so much of applied mathematics data analysis is built on numerical methods such as the ones that are covered in this course. Okay, so I've come to the end of today's material, but there's still a little time left. Are there any questions? Be sure to unmute yourself if you do, or you can ask in the chat. Okay. Oh. Oh, yes, actually. For the past 3 summers, I have been what's called a summer faculty research fellow at the Naval Research Laboratory. So I work with one of their research scientists who is a physicist by training, on developing numerical methods for various wave propagation problems. For example, the latest one, modeling of sound waves in the atmosphere. So for our collaboration, he tends to cover the theoretical side of understanding how solutions of these equations behave. These are partial differential equations. And then I contribute the numerics to help verify the theory and also develop fast solution methods. I a few years ago, the other lab I mentioned, Army Corps of Engineers Research Center, that's located in Vicksburg. I went there back in 2017 to give a presentation about my research, and they expressed an interest in at the time in hiring my students. Five of my former students now work there, um, and they're still hiring. So there's definitely demand within Mississippi or also in the region. Another lab that's not in Mississippi but not too far away is Oak Ridge National Laboratory in Tennessee. There's good career opportunities there too. Okay. On the heels of my collaboration with Naval Research Lab, a couple of my students have since then have obtained summer internships. So NRL has a summer internship program, and one of those students went on to obtain a full-time research position there. So she finished her master's here, and now is uh, working on her PhD, sponsored by them. Yes, it's the NREP program. Okay. Um, oh, okay, the course website, you mean my website or Canvas? Okay. That is the correct link. Oh, try HTTPS instead of HTTP. And both are supposed to work. Like when I clicked on the link just now in the chat, it took me a page that gave me some warning, and I said click continue, and it took me to the site. So the site is running. If I check the link in Canvas, okay. I'm gonna edit the link in Canvas to make sure it uses HTTPS. Okay. Okay, I just edited it in Canvas. Okay, I'm not sure what's going on there. Are you on or off campus? Okay. Okay. At this moment, I'm off campus. So I'll just, tomorrow I will be on campus and I can check it there. But okay. Sometimes it does happen where something freaky is going on campus. Um, Not sure why. Okay, using USM public Wi-Fi. Oh, yeah, that's a possibility, unfortunately. Um, um, is there anyone who is on campus but connected by EduRoam instead of USM public who can check that? I don't know if that's
I am, and I'm actually in the math zone right now, connected to the Wi-Fi, and I can access your website without a problem.
okay. Interesting. Um, okay. I would hope that my site's not blocked by Campus iTech. If not, I'm gonna throw hands. Um, that's that's just ridiculous because they're the ones who literally administer the site. They're blocking their own sites, their own server if they're doing that. Um, and no, I would not put that past iTech. So, um, okay, well, and since I'm off campus right now, um, any USM student should be able to access the EduRoam Wi-Fi. So I would recommend trying that because that's the best Wi-Fi network to be using whenever you're on campus anyway, and instead of USM public. Okay. All right. I will look into that tomorrow just because that's something it's crazy that it's happening. But um, okay. Maybe USM public is being run by some other entity that's being stupid about it. I don't know. Okay. Are there any other questions? Okay. Well, it's 1 minute past time anyway, so I'm going to end the recording here, and I will try to get everything posted shortly, and I will be in the classroom on Thursday.